So welcome to our second session of QBronze workshop. And so today's instructor is Dr. Sabah. She's a scientist working at Marmara University. Her current research focuses on developing new quantum algorithms for scientific questions. And she got her PhD in 2020 from Marmara University Physics Department with her thesis on molecular dynamics under laser control. And she's currently coordinating Q-Turkey, and this organization aims to spread quantum information and build a quantum network in Turkey. She also delivers lectures related to quantum technology in her university and Q-Turkey workshops. So I will leave the floor to Dr. Sabah.
Thank you very much. Welcome everybody again to the second session to this QBronze workshop, which we have organized along with QTech. We are very proud of this workshop. Share my screen with you. Could you please tell me if you can see my screen or not?
Yes, we can see the screen.
Okay. My screen is flashing right now. When it stops, I will continue. Okay, so I guess you can see my screen right now, right?
Yes, that's perfect.
Okay, so yesterday Özlem has given the lecture about the basics of classical systems. He reminds you, she revised you the bits, and he introduced you the coin flipping game, and then she mentioned about the probabilistic states along with the probabilistic operators and the two probabilistic bits, you know, how to deal with the complex or composite systems in classical information. And then she conducted 3 different scenarios for an experiment, which is performed with photons. As you know, photons are not classical particles. They obey quantum mechanical rules. Therefore, when you do the experiment with not with a coin but with a quantum mechanical particle such as photon, your intuition doesn't align with the experimental result. Today we will continue from this part of the workshop. Our first notebook is Adamar operator. First we will get to know about the Adamar operator. You know, what is Adamar operator and how come it will help us to understand the experimental results of from the yesterday's lecture. In Qiskit, Adamar operator is defined as H-gate. As Özlem mentioned yesterday, we are using a circuit representation for quantum computation, and we are using Qiskit in this workshop. And in circuit representation, we have a quantum circuit, and we place suitable gates to perform the quantum computation. In this notebook, we will conduct 3 different experimental scenarios using Qiskit, and for the beam splitter, we will use Adamar gate. And for the first experiment, you will remember this schedule here. we have a photon source, which will be represented by a qubit, and a photon beam is released from this photon source, and it will hit the beam splitter. When a photon comes to the beam splitter, there are two different possible scenarios for this photon. It can be reflected to the photon detector through the photon detector here, or it can be transmitted through the beam splitter to the photon detector here. This is the first experimental scenario, and this is like a coin flipping operation. For coin flipping operation, there are two possible outcomes. Which first one was head and the other one was tail. Similar to that operation, here we have two possible outcomes for the photon. It can be reflected or it can be transmitted. Therefore, this is the quantum version. This can be seen as a quantum version of the coin flipping operation, which is performed by a beam splitter in a real optical experimental setup. These beam splitters are realized by semi-transmitting mirrors. Okay, so for the Qiskit part, we only need one quantum register because we only have one quantum source, one photon source, and after the measurement, we will only need to use one classical register or one bit. Our quantum circuit consists of these two components: one qubit register and one classical register. And for this qubit, we put an Adamar gate representing this beam splitter here, because similar to the beam splitting, Adamar gate provides two possible outcomes for an input state. We will see the details of the Adamar gates later in this lecture. And after Adamar gate, we will measure the outcome to see if the photon is reflected or transmitted. This is our quantum circuit. And after the execution, we can see the results. We are running this quantum circuit 10,000 times. Yeah, 10,000 times. This means that we are using 10,000 distinct photons, or we are using a photon beam, which includes 10,000 photons. Our expectation, can you guess our expectation? What should be the outcome for this experiment? After the experiment, I will count if the photon is transmitted or reflected. If the photon is reflected, then the outcome will be represented by 1, because its state is changed from this way to the other direction. And if it is not changed, meaning that if it is transmitted, then we will see it as a 0. Can you guess the outcome? I am using, I'm performing this this experiment with 1,000 photons. How many of the photons will be reflected and how many of them will be transmitted? Can you guess? You can write in the chat. Yes, it is a fair beam splitter or fair quantum coin. Yes, more or less 50% should be reflected and the other 50% should be transmitted. And when we perform this experiment, our observation is 51% is state 0, meaning that it's transmitted, and 48%, 49%, nearly 49% is in state 1, meaning that it's reflected. When you redo the experiments, the exact numbers will change, but the percentages will be nearly 50% each time. So this was our intuition as well. We were expecting to see the 50% of the photons in this photon detector, and the other 50%, other half, to see in this photon detector. And when we do the third experiment, the scenario was changing, and our intuition was not the way we are expecting. The results are not the ones we observed. So first of all, let's recall the experiment 3. For this, to this end, we are using 2 coin flipping operators, meaning that we will use 2 different Adamar gates. And after a photon is emitted from the photon source, it will reach to the first coin flipping. There are 2 possible scenarios for this coin, for this photon here. It can be transmitted or it can be reflected to the second path. There are 2 different paths here for the photon. It can follow either one. Let's consider the first possible path here. After it's transmitted, let's say the photon is transmitted, and after it's transmitted, it will be reflected through a classical mirror. This is not a quantum operation. So therefore, this mirror here does not change the state of the photon. So this part here, the photon is still in state 0. After after the photon have reached here, it's going to encounter a second coin flipping operation or another Adamar gate. So this photon can be transmitted again or reflected this time. So there are 2 possible paths for this photon to, follow. But if the photon is reflected from the first coin flipping operation or the beam splitter here, then we are here. We are following this path. Again, this means that the state of the photon is changed from state 0 to state 1, and then when this photon is moving along in the state 1, and it will come to the second coin flipping operation. Again, there are 2 possible scenarios here. This photon can be reflected into the state 0 again, back to the state 0 again, or it can be transmitted, meaning that it will stay in the state 1. So there are 4 possible paths for a photon to take. For a photon, it can be taken. The first one is following. The first one is state 0, coming here and being transmitted and transmitted again, and this photon will end up in detector B1. The second possible path may be that Okay, Ishil, I will clarify, but please let me finish the listing of the possible paths. The second possible path is when a photon comes here, it will transmit it, and then it will reflect it, meaning that it will end up in the B2 detector. And the third possible path is that when the photon comes here, it will reflect it, and then it will, say, transmit it, meaning that it will end up B2. And the fourth possible scenario is that the photon comes here, it will be reflected and reflected again, meaning that it will be end up in the B1. So to summarize, the photon can be reflected 2 times, the photon can be transmitted 2 times, or it can be reflected and then transmitted, or it can be transmitted and then reflected. There are 4 possible scenarios. The state 1 is transmitted or reflected. Okay, this is just a naming convention that we do. We say that we choose that this is state 0, and when the state comes to the, or the photon comes to the beam splitter, if it is transmitted, then the state is not changed, but if it is reflected, then the state is changed. So I cannot say that the transmission itself is being transmitted is state 1 or being transmitted is state 0, but transmission does not change the state, and reflection does change the state from 1 to 0 or vice versa. Is it okay? Okay, so when you begin with the state 1 here, then if it is transmitted, then you will see state 1 here. So let's perform this experiment in the quantum circuit. To this end, we will use 2 Adamar gates. We'll use 2 Adamar gates. The first one is representing the first coin flipping or the beam splitter here. The second one is representing the second beam splitter here, as you can see. So what's your, again, we are performing this this experiment with 10,000 photons. What's your expectation for B1 and B2? How many photons you will expect? How many photons are you expecting to see in B1 or in B2? As B1 and B2 are the detectors here. You can write your guess in the chat. You would expect half and half. Yeah, you would expecting half and half, but that's not the case. So why do you think it's not the case? As a classical beings, us humans tend to, expect to see 50% of the photons in B1 and the other 50% of the photons in B2, but our intuition is not, I mean, they trick us, our intuition trick us here, and our expectation is not correct. So why do you think this is the case? Do you have any idea? the exact experimental results are that we see all of the photons in B1 and none in B2. And why do you think is the case? This is the case. Okay, this could be the intuitive explanation, even though we are expecting them to follow one of four possible paths. They don't, and they end up they only choose two paths from four possible paths. It would be the case, then I would ask you why would a photon choose B1 over B2? Okay, we know a phenomena that's canceling out each other, or summing up to one another from the wave mechanics. A photon behaves like a quantum mechanical system, and in quantum mechanics we are dealing with these probability waves, which are waves in essentially waves, so behaves like a wave, so they can they will construct or destruct each other. So the photons or the probabilities of photons or the probability of a photon reaching to the B2 from two different paths are canceling each other out. Therefore, we are not seeing any photons here. So let's move on to the one-qubit system. For quantum systems are linear, and we are representing them with state vectors. For a qubit, there are only two possible states to be in. So therefore, we are representing these two possible states with two pure cats. The first one is called as cat 0, and the other one is called as cat 1. The matrix representation or the vector representations are shown here. The first one is the 1 and 0 matrix, and the second one, or cat 1, is 0, 1 matrix. And for qubits, we need to perform some operations on the qubits to manipulate them and store some information into these physical systems, and gain some information out or measure them to manipulate them to use them as a informational process unit. The first one is the NOT gate. The NOT operator or the NOT gate, which corresponds to the Pauli X spin matrix. There are a question here. Okay, for this system, what will be the result if the initial state is 1? You mean this one? Okay, so this is your task here. If the initial state would be the state 1, or here you see the state 1, then you will apply two different Adamar gates again, and you will gain an intuition, a quantum mechanical intuition for the experimental result here. But I can confidently say that you won't see 50%, 50%. Again, you will see all of the photons in one of the detectors. I won't say which one because it's the answer of the task. And at the other detector, you won't see any photons again. For the NUT operator or the X gate in the quantum computation, the X gate or the NUT operator changes the state of the qubit from one to the other. Remember that we have two pure states, ket 0 and ket 1. So when you have a qubit in ket 0 and you apply X, you will get ket 1 or vice versa. You can show that operation in short form, as you can see here, or you can use matrix representations and do the matrix math or linear algebraic matrix multiplication, and you can see the result is of course ket 1. And when you apply X gate to the ket 1, you will end up with ket 0 again. You can do the math here to see the inner steps. Okay. So since we are using the real numbers in QBronze, but the quantum computing is, quantum computing considers complex numbers as well. There are differences between X and NUT operator and X gate. The classical NUT operator is different from the quantum mechanical X gate or quantum mechanical NUT operation. Since we are using only the real numbers in QBronze, this distinction is not obvious, may not be obvious, but I need to emphasize that the NUT gate or the quantum mechanical X gate is not same as the classical one. For Adamar operator, sorry. For Adamar operator, the matrix representation is shown here. The importance of the Adamar operator is that Adamar operation puts a pure state into a superposed state. I will tell about the superposition later in this lecture, but to mention it very shortly, a quantum state can be in either ket 0 or ket 1, and it can be in a mixed state, in a mixture of ket 1 and ket 0 as well, which is called a superposition of the two pure states. There are some important aspects which I should emphasize here. Here you see a negative entry in the operator, which is different from the probabilistic operations. Remember that for the probabilistic operators, the entries should be non-negative, meaning that they can be 0 or positive numbers. And here we have a negative entry. This is the key explanation point for the cancelling out of experiment 3. Okay, so let's go back to the our experimental scenarios. For the first experiment, we were using only one coin flipping or beam splitter, meaning that we were applying Adamar only once. When the photon is state 0 and comes to the coin flipping operation or beam splitter here, we are applying this Adamar gate on cat 0. H cat 0 here is the mathematical representation of this experiment. When you use the matrix notation here, you end up with 1 over square root of 2. Can't you hear me?
Yes, we can hear you.
Okay. Okay, let's give me a minute. Right. You are end up with probabilities of these two states here. The first entry is 1 over square root of 2. The second entry is also 1 over square root of 2, meaning that state 1 is the amplitude or the coefficient of state 1 is 1 over square root of 2, and the other one, the state 0's coefficient is 1 over square root of 2 as well. What is the meaning of this square root of 2 or 1 over square root of 2? These are not the probabilities themselves, but the amplitude of probabilities, meaning that 1 over square root of 2 is the square root of the probability. So when you square these numbers here, these entries here, you get the probability of that state. So when you begin with state 1, you get this minus sign here. This is just this is not the probability itself, but the probability amplitude, meaning that this negative sign will have some impact on the experimental results, but when you measure or when you observe the system, to gain meaningful or observable numbers, you need to square these entries. As you can see, the negative sign is important here. But when you try to guess the outcomes, you will square these numbers, both this coefficient and that coefficient, and you will end up with 50% in each detectors. They are the probabilities, the squares of the entries. As I have said, they are the entries of the states or the coefficients of the pure states are called probabilistic amplitudes, meaning that they can be negative or they can be complex as well, even though we are not considering complex coefficients in QBronze. They can be negative and they can be negative, and this will this ability to be negative will have impact all over the computation. So this is a new computational paradigm. So this teeny tiny difference of that entries can be negative has huge impacts on the outcomes or the computational power that we have in the quantum mechanical systems. There are two important states that we are using too frequently. Therefore, we gave them specific names. The first one is cat plus, the other one is cat minus. Cat plus is the state which we obtain when we apply Adamar gate to the cat 0. Its entries are 1 over square root of 2 and 1 over square root of 2. And cat minus is the one we get when we apply Adamar to cat 1. And the only difference is that it has minus sign in the second entry. These are only the naming conventions that we do, but we are using these states too often. So we need to, or we want to give them their specific names to our convenience. Okay, so this is the sum up for until now in the quantum computation. Quantum states are represented by a vector. Their entry can be 0, positive, or negative. And these entries are amplitudes. They are not the probabilities themselves, but the probabilistic amplitudes. And to get the probability or the probabilistic numbers, you need to square these amplitudes. So, do you remember the probabilistic state? Not every vector you write is a probabilistic state, but there is some rules that probabilistic states or that these vectors should obey. Similarly, here we have quantum states or quantum vectors. Yes, their entry can be positive, negative, or 0, but they still have some rules to obey. Let's move along to the quantum states. To determine if a vector is a valid quantum state, we have one rule, and it again is related to the probabilistic theories. Sorry. Okay. It's again related to the probabilistic equation. So we are considering closed systems, meaning that there are no energy going out of the system, or there is no energy getting into the system. Therefore, our quantum system is closed, and everything possible should be considered in the quantum state vector. Meaning that you should, or you have to get all the possible information for that quantum system by using that one vector, and the only that vector. Meaning that when you sum all the possibilities of that quantum state, you will end up with one. What I'm trying to say is that you will remember that for a quantum state, these were the quantum probabilistic amplitudes, And when you square them and sum them up, you should get 1 because they are closed systems. And everything possible, every state possible should be representing here in this vector. If you are, if you end up with a result other than 1, then this. So let's check these two these two vectors if they can be if they can represent a valid quantum state. So the first one, the entries are 1/2 and 1/2. So the amplitudes for ket 0 and ket 1 is 1/2, and the probabilities to measure this system in ket 0 is 1/4, and it's the same for ket 1. And when you sum this up, you will end up not 1, but 1/2, meaning that there should be other, there could be other possible states, which shouldn't be the case for a closed quantum system. Therefore, this is not a valid quantum state vector. Similarly, you can check this one as well. So there is one rule for this quantum states should obey. Their amplitude squares, their summation of amplitude squares must equal to 1. Or to use more fancy words, a quantum state can be represented by a vector of length 1 or vice versa. Do you have any questions? Oh, I have a question here. What does intermediate measurement mean here? Which intermediate measurement? You mean the experiment 2, I guess.
And this question
if you mean the
is at the beginning of the lecture, so maybe, yeah, I guess it was third experiment.
Yeah, okay, the third experiment. Where was it? Not here. Okay, there are no intermediate measurements here. The only measurement here is at the end of the experiment. But there is an intermediate measurement in experiment 2, scenario 2, and we will see it, we will examine it in detail later in this lecture. Okay, so yeah, sure. Okay, so the length, when we say the length, we mean that for a vector to calculate its length, you square that vector, and, or in other words, you scalar product it with itself, and then take the square root of the number you get, or the scalar you get. In bracket notation, we are representing the scalar product, as you can see here. And if the length of a vector is 1, then we can omit the square rooting part of the length calculation. Okay, so for the quantum operators, we have another rule for the quantum operators. As for the probabilistic operators, not every square matrix is a quantum operator, but these quantum operators should obey some rule, which is preserving the length of the quantum states, meaning that before and after you have applied this quantum operator, the length of the quantum state should stay 1. Or in other words, you shouldn't gain or lose any information or any possibilities before and after you apply this quantum operator. In technical terms, these kind of matrices called length-preserving operators or length-preserving matrices. Okay, so to check if a matrix is can represent a valid quantum operation, you can use a quantum state, a valid quantum state. You can apply that matrix on your quantum state and then check if the length of that quantum state is preserved or not. Okay, let's move to the visualization of a real-valued qubit. Again, we are using only real values here in QBronze. In quantum computation, the complex numbers are considered, and the amplitudes for a quantum state can be complex numbers. Then for a whole picture, we need to use something called block sphere. But for simplicity in QBronze, because this is an introductory workshop, we are using only real valued qubits, and therefore the unit circle is enough for us to represent a quantum state. We are using, in this notebook, we are using some methods from PyPlot library of Python. You can check the Python drawing notebooks to revise your information or your knowledge on how to plot in Python. So in quantum states, we can have negative entries. And these are the negative numbers, as you can see here. So let's draw them. These are the axes of the unit circle. We will place the state 0 in the horizontal line and state 1 in the vertical line. This is the origin, and these are the dots corresponding to 1, 0, 0, 1, minus 1, 0, and minus 0, minus 1 coordinates on the Cartesian coordination. And these are the vector representation of those coordinates on the Cartesian coordination. Sorry, this is the task. So let's go to the unit circle. So this is a unit circle. The unit circle is a 2D shape whose radius is 1. And since our quantum states are representing by the vectors whose lengths are 1, we can use such a representation to visualize our quantum states. So let's draw a quantum state vector given here. 3/5 and 4/5 are the entries. So this is our unit circle. So this the horizontal axis is chosen to represent ket 0, and the vertical axis is chosen to represent ket 1. And this is our vector representing the v vector. The entries are 3/5 and 4/5. These are the assistant functions which we have provided you to use for visualization, quick visualization on unit circle. Okay, so this, as you can see, these are the cosine and sine correspondings to the vector here. Okay, so the angle of the quantum state with this ket 0 axis is A. The cosine of that angle yields the ket 0, the amplitude of ket 0. The sine of that angle yields the amplitude of ket 1. And the angle for quantum states are quite important. So let's see how to make them understandable. So the positive angle is defined as the angle between this horizontal line or ket 0 axis with the vector itself. To build a random quantum state, you can choose a real value. You can choose a random angle between 0 and 2 pi radian, and then using basic trigonometric functions, you can build a random quantum state. To calculate the amplitude of ket 0, you should take the cosine of that angle, and to calculate the amplitude of ket 1, you can use the sinus function of that angle you have produced. Okay, so that's it. Sorry. Yes. Okay, before moving to the superposition, do you have any questions? Yes, I will give a break right now. Sorry. Okay, so let's take a 10 and see you at 3:05. Hello again. Let's continue. Okay. Please tell me if you can see my screen or not.
Yes, we can see your screen.
Okay, so we will continue with superposition. This is a concept which has no classical counterpart. A superposition is being in for a physical system. Being in superposition means that being in more than one possible states simultaneously. This is a quantum mechanical concept or phenomena. This has no classical corresponding. So to understand it classically, it's not quite possible. We can think about it as probabilities for a coin. For a coin, we may think that when the coin is flipped, when it is still in the air and doing its flips, then there are still some possibilities, and the process is not over yet. The coin is still in the air, and you can think that system in that moment that it's in, say, both states. It can be heads or tails with some probabilities. The superposition in quantum mechanics can be thought as the coin in the air, but it's just an example. It's just an explanation. The real nature for quantum mechanical systems, they really are in more than one possible states simultaneously. This is the real nature of quantum mechanical systems. This is hard for us, for human beings, to wrap our heads around, but this is the case. This is how nature works. And we call this phenomena as superposition. I repeat, the superposition is being in more than one possible states simultaneously. This is a quantum mechanical concept, and this has no classical corresponding or classical counterpart. This is a quantum mechanical or quantum concept. To understand this, the effect of superposition, we need to look at the third experiment again. For the first part, after the Hadamard gate is applied to the photon, or the beam splitter splits or acts on the photon, then we get this state vector. After the first beam splitter, our state vector, our qubit, is in this state. And this is a superposed or superposition state, superposition of ket 0 and ket 1 state. This vector is in a superposition of ket 0 and ket 1, or state 0 and state 1, meaning that the photon is both in state 0 and state 1 simultaneously. And their amplitudes, these states' amplitudes, are 1 over square root of 2. They each are. In this case, they are equal to each other. in general, it doesn't have to be that way. I mean, the amplitudes of superposed states can be different, but in this experiment we have equal amplitudes. But in this step, the photon is in superposition, meaning that it's both in state 0 and state 1, with amplitudes of 1 over square root of 2 and 1 over square root of 2, respectively. This can be hard to understand, or we cannot, gain any meaningful outcomes, or we may not gain any intuition from this at the beginning, but you will get used to it. Believe me, if this is your first time, about superposition, you will gain more intuition about it over time. And again, this is not a classical phenomena. This is fully a quantum mechanical nature of the particles. A quantum mechanical particle or a quantum particle can be and is in more than one state, more than one possible states simultaneously. This is the physical reality for the quantum mechanical particles. So to break this vector into the bracket notation, we can write this formula here. It's 1 over square root of 2 times ket 0 plus 1 over square root of 2 times ket 1. And after the second step, I mean the Adamar is applied for the second time, meaning that after this operation we are here in the timestamp. Okay, when you apply Adamar to V1, you are applying Adamar for the second time here, and this is the open form of V1, and you can write. You can open that parenthesis by writing Adamar into in front of each ket here. You have two terms, as you can see here. The first term contains Adamar on ket 0, and the second one contains Adamar on ket 1. Adamar on ket 1. And let's split these two terms. When you apply Adamar on ket 0, you end up with plus sign here at the in front of ket 1. But when you apply Adamar on ket 1, you get this minus sign in front of ket 1, and we need their summation. So when you sum these two terms up, the amplitudes of ket 0 sums up, but the amplitudes of ket 1 cancels each other. So this is the mathematical explanation of the third experiment's results. So we end up with ket 0 at the end of the second, after the second Adamar gate application, meaning that we will only observe the photon in state 0. And for a photon to be in the state 1 after the second Adamar operation is 0. There is no photon in state 1 after the second Adamar operation. The other the canceling each other or summing up to one another are called interferation for the wave mechanics. So if two waves are sum up to one another and they get their amplitudes bigger, then we say that they are constructively interfered. And if they cancel each other up, and if they cancel each other out, then we say they are destructively interfered. So the waves are interfering with one another, and if they sum up to a bigger number, then they are constructive. This interferation is constructive, and if there is a destruction or canceling each other out, they cancel each other out, then there is a destructive interference. Are there any questions so far? Okay. Okay, so for the probabilistic systems, they are classical systems, and we don't have any negative entries. So the probabilities are only only give their effects in a positive way, meaning that they can only sum up. But in quantum mechanical systems, since we have negative entries as well, they can cancel each other as well until the effect of that ability to be a negative number will affect everything along the way. So I am checking if there's something that I should also mention. Okay, so let's move to the measurement. What happens when we measure a quantum mechanical system? Until the measurement, a quantum mechanical system can be in a superposed state. I repeat, meaning that it is in more than one possible states with non-zero amplitudes. But when a measurement is performed, then the system will choose one of the possible states. And this phenomena is called collapsing. In technical terms, when you measure a quantum mechanical system, the system collapses into one of the possible states. And this way, all of the unmeasured states, all of the amplitudes of unmeasured states vanishes, and the amplitude of measured states becomes one. So let's say that we are dealing, or we will observe a quantum state with this vector. This is a valid quantum state vector, and there are two possible outcomes here. The amplitude of the ket 0 or state 0 is minus square root of 2 over 3, and the amplitude of state 1 is 1 over square root of 3. And when we measure this quantum state, we won't see these numbers themselves. We will see either state 1 or state 0. And there is probabilities for us to see these outcomes. When you measure this state only once, you may not determine, you cannot determine these probabilities, or you cannot observe these probabilities in action. But just by looking at the experimental results, to say that you will end up with state 0 or state 1 with that probability or this probability, you need to, construct the theory of the experiment. But if you want to examine the system just with experiments, you should do the experiments again and again enough times to gain an probabilistic knowledge or information from the experiment. You should redo the experiment many times, as many as needed, to gain these numbers. So when you measure this quantum system, you will see either state 0 or state 1, meaning that after the measurement, your qubit collapsed into the measured state. So if you, let's say you measure state 0, then your, then your state vector after the measurement is this one. Or let's say you measure state 1, then the qubit vector or quantum vector after the measurement is this one. If you see state 0 after the measurement, we say that this state vector collapsed into state 0. Or if you see state 1, we say it collapsed into state 1. Do you have any questions about collapsing or measurements? This is really an important aspect of the quantum mechanics. You cannot observe the quantum states in superposition until, meaning just by taking one measurement. You cannot observe them into superposition just by measuring them once. Okay, so let's go. Sorry. Let's move to the second experiment. In the second experiment, we have this intermediate measurement here. And if we measure the photon here, then the photon or the qubit collapsed here. But if this is not the case, then the photon is, or the qubit is, the photon is the second coin flipping or Adamar gate is applied onto the qubit. The second one is here. So in this experiment, so we begin with state 0 and we apply Adamar gate once. Then the current state vector is, as you can see, the one here. And after that, we measure the statement. We measure the quantum state. If we measure state 1, then this is the end of this path, meaning that we are, or the photon is, the photon ends up at the detector A. But measurement result is 0, meaning that we are on this path. Then the photon will be faced to another coin flipping operation, meaning that a second Adamar gate is operating onto this photon. The probability of seeing 0 here is 1/2. Therefore, after applying Adamar again to the cat 0, we end up this quantum state here. And after that, we have another measurement. The 1/2 can be the 1/2 can be absorbed in state 0, and the other half can be absorbed in state 1. But we have begun with half probability here. Therefore, we have 1/4 probability to see the photon in state 0, and the other and 1/4 probability to see a photon in state 1. To implement the second experiment using Qiskit, we will use a classical if state provided by Qiskit to us. We use C-if or classical if statement or method to represent the intermediate measurements during the quantum circuit or quantum experiment. Here is the code part. Let me show you the quantum circuit. Okay, so we put an Adamar gate here. After that we take a measurement, and if this measurement is 0, then we will apply another Adamar gate. This part here is represents the condition, the if condition, and the numbers you hear are the first 0 is the index of the classical register, and the second one is the value of that register, meaning that if you see 0 in the classical bits indexed with 0, you will apply Adamar gate, a second one, and then you will measure again. So what's your intuition? What should we see after the execution? We are using 1000 qubits. We are running this experiment 1000 times. How many times you will see, or we will see 0, and how many times we will see 1? What's your guess? Please write in the chat. Let me show you again this part here so that you can guess more easily. We have begun with 1000 photons, you may say. How many photons we'll see in 1, and how many photons we'll see in 0? What's your expectation? Yes. 3/4, 1/4, 0.75 in 1, 0.725 in 0, 1, 750, 0, 250. Yeah, these should be the numbers, one or more or less. Okay. Okay, we have observed the state 0 246 times from 1000 photons, and 754 times over 1000 photons. Corresponds to more or less, or getting close to 25% and 75%. Do you have any questions in that sense? Sorry. Okay, so operations on unit circle. So we can visualize the operations or the effects of operations on the unit circles as well. So let's begin with representing cat 0 and cat plus on unit circle. Okay. Let's give a minute to the notebook to run that code. Okay. So remember the unit circle. The horizontal line was cat 0. It was representing cat 0. The plus cat plus is the one with angle pi over 4, 45 degrees, or in other words. The cat plus's entries are 1 over square root of 2 and 1 over square root of 2. This corresponds to the 45 degrees in this unit circle. So remember these two states. And similarly, I will show you the state 1 and state minus as well. State 1 is the vector here, and state minus is the vector here. Its amplitude of cat 0 is the same as the one of cat plus, but the amplitude of cat 1 has a minus sign in front of it. So can you guess the quantum mechanical operation which maps cat 1 to cat minus, or maps cat 0 to cat plus, or vice versa? Can you guess the quantum mechanical operation which maps cat 0 to cat plus and cat plus back to the cat 0? Or do you recall the quantum mechanical operation? Which one was that? Okay, so I have told you that for a random valid quantum state, you can choose a random angle theta between 0 and 2 pi, and the quantum state is cosine theta and sine theta. This is a random valid quantum state. So let's investigate the rotation with Ry. The Kiskit method to use rotation along the y-axis is Ry gate. And to rotate a qubit from a state to another one, say a theta, say a theta or some angle, you need to provide 2 times or double of that angle into the casket. This is because of the fact that we are using here the real valued qubits, and in reality there is pi angle on Bloch sphere between cat 0 and cat 1, but here we are using unit circle. So in this case we have pi over 2 pi over 2 radians in between cat 0 and cat 1. This is why we need a 2 coefficient in front of the angle. You'll see that this operation is of course a rotation. I will mention that in a little bit later. Okay, so we begin with let me show you here. For this measurement here, we begin with cat 0, and we rotate the quantum state by 2 pi over 3, meaning that we rotate this along this counterclockwise, and we end up with some superposed states. And after measurements, we can see this probabilities here. As you can see here, we have measured nearly 20% of the 20% of the qubits in state 0, and the other 75% of the qubits in state 1. Okay, let me show you the state before the measurement. Okay, we begin with the state 0 in the circuit, and when we rotate that state 2 pi over 3, we end up with this vector here. Okay, we have 2 more notebooks. The first one is rotation, and the second one is reflection. The quantum operators or quantum operations can be seen as rotations and reflections as well. And to this end, we will investigate the rotations and reflections in details. And let me run this part as well to gain more time. Okay, we are waiting for the notebook to run these codes here. And again, I'll show you the representation of cat 0 and cat plus. And then we'll discuss if we continue to apply that operation which maps cat 0 to cat plus, which state will end up with. Let's say we begin with cat 0 and we apply a rotation to gain cat plus. If we apply that same rotation again, which state we will get after the second one, and after a third one, after a fourth one. These are the possible 8 answers to that question. Let me repeat my question. We begin with cat 0 and we apply a rotation to get cat plus. This is our rotation. So we rotate our state by pi over 4. Let's say we apply that rotation again. Which state we get? This is our question. And these are the answers. Which state we will end up with? What's your answers? What's your guess? Again, this is a rotation. You can write your answers in chat. Do you mean axis? No, I mean the states. We begin with cat 0 and we apply a rotation which rotates our states by pi over 4, and we end up, after first rotation, we get cat plus. If we apply that rotation again, which state we get? Okay, cat 1, right? Because this is not a reflection, this is a rotation. When you start with cat 0 and you rotate your state by pi over 4, you get this vector here. When you do that again, that same rotation again, you will rotate your state by another pi over 4, and you will get state 1. So this is the matrix representation of rotation by pi over 4. This is quite similar to the Adamar operator, but it's not the same. They are just similar. So okay, so this matrix is the general definition of a rotation operation on unit circle. So when you need to rotate your state by theta, you can use this rotation matrix. But if you want to do that using Qiskit, you should use RY gate and provide the gate with with double of the rotation angle. Okay, so our last this one can be killed. Our last notebook for today is reflections. We have another type of quantum operations which are classified as reflections. They are similar to rotations, but they are not rotating the states continuously along one direction. Instead of they are rotating the state, they will reflect the state upon a chosen or a convenient axis, which is called reflection axis. Okay, let's begin with remembering or revising the identity and Z operators. An identity operator is the operation which changes nothing about the state. Its matrix representation is shown here. And for the Z operator, this is the first time you see the Z operator here in the QBronze, but it's quite similar to the identity operator, apart from that minus sign here. And as you guess, that minus sign has huge impact on the calculation. So let's consider this quantum state. And when you apply that Z gate on this quantum state, you gain this minus sign, or in technical terms, local phase in front of cat 1, amplitude of the cat 1. Let's draw these two states. We begin with U, which is this vector here. When you apply that Z gate, you get U prime. And when you apply Z to U prime, and let me give you a hint, Z is a reflection. Can you guess, when you apply the Z for a second time, can you guess the result? You can write your answers in the chat as well. So let me rephrase. Here in this scenario, we begin with U, and we apply Z gate, and we get U prime. I am asking that what we will get, or can you guess the result of the second of the Z gate operation? Sorry, can you guess the result of the of operating the Z gate for a second time? What's your intuition? It can be 0, it can be U again, it can be 1, it can be U prime. What's your intuition? What's your guess? What should I get, or what will I get when I apply Z for a second time? So Z is not a rotation, but it is a reflection. When you apply the Z gate on U prime, you will get U again. For a third time, you will get U prime. Fourth time, you will get U, meaning that Z is reflecting the states over X axis. Or in other words, the reflection axis of Z is this line here, cat 0, or X axis. So let's check Adamar operator. First of all, let me remind you that when you apply Adamar to 0, you'll get plus. When you apply Adamar to plus, you'll get 0, meaning that 0 will be mapped to plus, and plus will be mapped to 0 by Adamar. And similarly, 1 will be mapped to minus, and minus will be mapped to 1 by Adamar. And this was this one was the plus and 0 cats. These were the minus and 1 cats. So I will give you a hint, as you can guess already. Adamar is a reflection operation. So can you guess the reflection line or reflection axis of the Adamar? Meaning that when we begin with, let's say, 1, the first operation of Adamar will map our state to minus. The second one will map back to the 1. The third one will get minus. The fourth one will get 1. We are reflecting these states over a constant line, which is called the line of reflection of Adamar. Can you guess the line? You can express it with some degrees. And that degree or that angle can be the definition of the angle, the line between this axis, this horizontal line. This vector, the angle of that vector is pi over 4. This is pi over 4 angle. And we begin with 0 and apply Adamar again and again and again. We are mapping these two vectors from one to another. So yeah, this is the axis with pi over 8, right? Because this whole angle is pi over 4, and cat 0 and cat plus is mapped to each other by consecutive operations of Adamar, meaning that you should, you are reflecting this state over the line of pi over 8, the line with pi over 8 angle. Okay, is this obvious? Is this understandable, or do you have any questions? So this is the summary of 3 important or often used quantum operators, line of reflections. The Z operator reflects a state over x-axis. Adamar operator reflects the state over this line, meaning that the line with pi over 8 angle. And NOT operator reflects the state over y is equal to x-axis, x-axis, or the line with pi over 4, the line with pi over 4 angle. And this is the general definition for reflection operator. If you want to express an arbitrary a reflection operation with an arbitrary angle, then the matrix representation of that operation is shown here. So do you have any questions? For Qiskit part, there are different realizations for different reflection operators. The commonly used three reflections are here: Z operator, NOT operator, and Adamar operator. But you can build your own reflection operator or reflection unitary in Qiskit as well. So today we have seen Adamar operator, and we introduced the qubit systems and quantum states. We have seen how to visualize a real-valued qubit. We have mentioned about the superposition and measurements, and we investigate the operations on unit circles, and we have studied about the rotations and reflections as well. Tomorrow you will continue with Özlem by studying composite quantum systems, and you will learn about phase kickback phenomena, and you will examine the entanglement and superdense coding along with quantum teleportation algorithms. So if you don't have any questions, I will end this lecture here. We have another mentoring session tonight on Discord. It will start at 9 p.m. 9 p.m. Turkey 9 p.m. GMT +3 Istanbul time. In Istanbul time. So why did we have double the angle while coding? Which one you mean? You mean this one? If you mean this one, this is the case. This is the difference between rotation and the reflection. Before. Okay, you mean this one, the rotation one, I guess. Yes, okay. So where was the note? Okay, this is due to the fact that we are not considering the quantum mechanics. We're not considering the complex numbers here. Let me find that note to show you. I guess it was in the other notebook. Okay, so this is the part I was looking for. In reality, or in a whole scenario, we have Bloch sphere, which we are not considering here. We are not examining the Bloch sphere in this workshop. But in Bloch sphere, the states 0 and 1 is placed on the poles, the Z poles of the Bloch sphere. The poles between, therefore the angle between state 0 and state 1 on the Bloch sphere is 180 degrees. But here we are using unit circle, and the angle between state 0 and state 1 in this representation is 90 degrees, not 180 degrees. This is why we multiply the angle by 2, because in reality it should be 180. It should be double of the theta here. Okay, any other questions? Okay, so you should be able to solve your first homework. You should be able to see your first homework on Canvas, and you should be able to solve it on Canvas. If you cannot see your homework on Canvas, please notify us so that we can check the system. You will have 1 week to complete your homework, complete your first homework. Today, your second homework is published, but you cannot see it until you have finished your first homework. To finish your first homework, you should obtain at least 10/20 in your first homework, and to gain your certificate, QBronze certificate, you should gain at least 70 points over 100. When you complete your homeworks one by one, you will see the next homework. You can try as many times as you want to solve your homeworks, but the deadlines are solid, and each homework has 1 week duration. If you have any questions about the system or the certification process, or questions or tasks, I highly recommend you to complete the tasks to gain the basic knowledge on the quantum states and quantum systems. I highly recommend you to complete the tasks. If you have any questions about any aspects of the QBronze, please just ask us on the Discord, and we will be online at 9 p.m. Turkey time.
And I would like to say thank you to Sabah. Even though she was sick, she used every minute of training efficiently. And
Yes.
we hope you all enjoy. So see you tomorrow.